Let's get started. We were in this kind of middle chapter of the lecture, which is about unsupervised learning. And unsupervised learning is very important because in many occasions you just don't have the answers yet, right? That's the big problem with supervised learning. You first need to ask a million people to give you all the answers, a million images of this is a cat, this is a dog, to just do this one task. It would be so much better if you could do useful things with the data alone, right? And that's what unsupervised learning is. Hopefully if we can do that, then on top of it, we can do better learning. So maybe we can do unsupervised learning to find good features, such that then on top of these features, we can do better machine learning. We maybe need much less labels, or we can do many different tasks. That's another very important goal in unsupervised learning. So the journey we took was that we had k-means clustering. That was the most important thing. You do grouping of your data. That's also kind of a way of finding new features, right? Because for each cluster, a cluster has a name. So now for each data point, you were able to assign it to a cluster. So now you have learned this a kind of a type, which is one kind of new feature for each data point. Then we saw that this is basically the same thing as a matrix factorization. There we saw that we can factorize data. So if the data comes in a matrix form, then we can factorize that into a product of two matrices. That was a very successful technique, and we will keep doing that a little bit today. So what we've seen there is, for example, the recommender system, and then the last thing we saw is you can factorize your matrix if it comes from text data, or like items appearing together, basically. Two words appearing together, or a movie and a user appearing together, right? Things which happen to occur together in the real world, just to learn from that, from this co-occurrence, to learn from this observation, without somebody having really manually annotated them. That's a very useful principle, and we saw that we can do matrix factorizations. So let me just remind you what kind of formulations we did for that. We had given data X. We tried to approximate that by a product of two matrices. That was so a matrix like this. It's maybe a narrow matrix. So something like this. So we had like k factors in between. These are called the latent factors. And the thing we want to factorize, so the x has dimension d times n. So which then means that here you have d times n. And these matrices here, we will be giving them the names w and z transpose. So that was matrix factorization. So the data is a matrix X. It's not so clear here what are data points and features. So this is just in general. If your data is a matrix, then you can do this. So now what are your rows and columns? What are their meanings? That depends on your application, right? So what we're going to do today is we're going to do dimensionality reduction. And we are again going to use this idea of using factorizing our big data matrix into two parts. So for us today, we're going to start again with data points. So we have a big data set. We don't have labels. And the points for us today, they will live in d dimensions, and they will be the columns of this X matrix. But think of this like in the recommender system. So there the data had a different interpretation. But today we will think of given data set of n data points, and each data point is in d dimensions. So what we're going to look at is called principal component analysis. So that's what PCA stands for. And to do that, we need to recap just briefly what is it, this singular value decomposition. So that's the plan for today. And actually, after this week, we will have 3 more weeks. Then we will start on neural networks with Rüdiger Obanke. And also the exercises in this week and next week, we will keep them very small and light so that you have enough time to focus on your projects. Also, who of you got my email on the office hours we do today and Thursday from Moodle? Announcements from Moodle. I think in the news forum you should get the announcement. Maybe not. So, but you got who got the previous announcement like a month ago from the news forum? I think some people got it. Okay. So anyway, in the Moodle, so please really use the discussion forum to discuss your questions on the projects and the exercises with the TAs, also technical problems. This is the best thing because then we can the answers will be there for everyone. So it's much better because there's so many of you. Okay, principal component analysis. So this is really not very hard. So if you're very familiar with linear algebra, what an eigenvector is, what a singular vector is, then this is a bit of a recap for you in the first hour, and in the second hour I'm going to show you the important application of how to use SVD to actually do dimensionality reduction of a data set. So the data set is X, and what we're trying to do is, again, we have d-dimensional input points, so the columns of X. We want to kind of project them into a lower dimensional space. So because we think D is still too large, so can we find a much smaller dimensional space with like fewer features, which has similar properties as the original data set. So I want to replace my D features by K features. So K much smaller than D. Let's see if we can do this. So that's the goal of PCA, to kind of compress your data from every point having D to every point having K. So remember, this is your original X. What you would like to do is to get a new X prime, which only has K features, but still n columns. That's our goal. Why is this interesting? So we will see this later, but there are kind of two main reasons why this is useful. On one side, of course, it just compresses your data. So when the D was very large, and now if you can just work with K features, then that might be an advantage. I would actually not recommend that so much for general machine learning tasks, so maybe better keep your original features if you can. I would only compress your data if you really have to. I mean, sometimes it might be a good idea for reasons, for example, of interpretability or other reasons. But compression is one interesting property we get from the SVD. The other property is that we kind of try, it's a probabilistic interpretation, and we are looking to decorrelate our input data. Maybe previously we had lots and lots of features, but many of them were kind of expressing the same thing. So this is the second thing that the PCA does. It finds you new features, K of them, which are kind of independent of each other. So you found new features where everything is decorrelated and independent of each other. That's what we would like to do, and we can see that both properties will actually lead us to the same formulation, which is the principal component analysis, and that's what we're going to do today. So that's kind of the goal. It's very related to the matrix factorizations, and that's what you're going to see. Yeah, any questions so far, or anything else? Something unclear? Then let's dive in. So the data matrix X is given. So it's D by N, D rows and columns, and so the SVD is this formulation here. I'm sure all of you have seen it. You should have, so that you can write any matrix X, even if it's rectangular. You can write it as this product of three things. So it's not surprising yet, except if you say that these things have some properties, because otherwise I could just write x times identity times identity. That's not what we want. But these three matrices have a very special structure, and so the u and v is something we want to discuss first. They will be orthogonal vectors, which correspond to this intuition at the beginning that we want things to become independent. So if you remember what the basis is, then that's the intuition for the columns of U, but don't worry, we will get to that. And the S matrix will be diagonal. So for now, for simplicity, I will just assume that the D is a bit smaller than N, but this doesn't matter. But just to keep things simple, let's say D is smaller. Otherwise, what could you do otherwise? What would you do if the N is smaller? Well, then you can do the same thing for the transpose, or everything I will say today is actually still true. So, okay, what are the properties of this U and V, and how do we obtain this decomposition? So before we rewrite it in detail again, I want to clarify the definition first. So what's important to say is that the U matrix has two properties that together is called, or to be a unitary matrix, and what that means is two properties. First, the columns are orthogonal, and second, the columns have length 1. So that's basically saying that the matrix is orthonormal, which is these two properties. So, and unitary is the same thing. So that you could actually also do this for complex numbers, but that's not what we want to do here. In machine learning we always have real numbers. Everything is fine. Nothing imaginary coming up. Okay. So what does it mean to have this orthogonality property? So what we assume is that the matrix times itself is the identity. That's what's written in the first line here. So that's very simple. So there are two ways of writing it. So is it visible enough, or should I turn off the light here? Shall we try without the light? That's maybe a bit dangerous. No, that's worse. Something like this? Is it better? No? Same. Okay, it's a bit dark. Okay, so we want to have these properties. So let's look at just the U matrix. The first thing is saying that the rows of U are orthogonal. Why? Because this expression here, if you think about what it is, it's saying that I pick a row and I pick a column. So what that means is the ith row of U, that's this element. If I write these two dots just meaning any column, makes my notation a bit easier, then this times ui, for uj, so for two indices I and j, this is 0 or 1. So it's 0 if I is different from j, and it's 1 if I is equal to j. That's what this is saying, the first expression here. And the second thing is, and this expression here is saying the same thing about the column, which I could write as column I. That's a column vector. I transpose it to get a row vector times the column j. And same thing there. So these are what I wrote here. These are the two expressions we have here. That's very easy. And the same thing for the columns. The same thing about V. So we want the V rows to be orthogonal. And so why does that mean that also so what's not so clear here is, okay, rows are orthogonal. So why are the columns orthogonal as well? It's not directly obvious, right? So, but this is we have a small proof here. So, and what it's saying is that if you have this for the rows, which is written here, it's claimed that then you also have it for the columns. So does anybody see why this is the case? So let's look at it. So here, this is what we assume. U times U transpose is 1. So what this gives us is that this is saying that U transpose is the inverse of U. So I can use this inverse matrix because the inverse is defined such that when I multiply a matrix with its inverse, I get 1. So therefore, if I write that U transpose is the inverse, which I have done here, then I will get the identity. So, and now I saw that also U transpose U is the identity matrix. Okay, so what I did here only works for square matrices, because otherwise you will never have this property that the inverse is actually exists, right? So, but if you have a square matrix, then this thing can have an inverse. And then if you see that it has this property here, then you see that, oh, the inverse is actually U transpose. Because if I use that, I get the identity. So you have found the inverse. So that's all. Okay, maybe I confused you a bit. Just to say that when you have a square matrix where the rows are orthogonal, then also the columns are orthogonal. And then what is about this business with the length? That's very easy. So because this is not just orthogonal, it's just saying that the matrix is 0 in the off-diagonal entries. That means every row I, which is different from J, they get 0 in a product. That means they're orthogonal. That's the green case. Now the case here with the 1, that's saying that the length is 1, because that's saying that any row I take and multiply with itself, I get 1. So therefore, so that's what you mean. Both properties together mean that my matrix U is orthonormal. So, and that's what we assume here. And we assume it not only for the U matrix, but both for U and V. Okay, so that's talking. Let's go back. What we want to do? We want to write this as a decomposition, and we claim this is possible with the U being orthonormal and the V being orthonormal. So let's actually write the whole thing. So we have X, and now I don't need to approximate, but now this is really equal. So this is an equality. It can be written as this decomposition, U times S times V transpose. And let's see about the shape of these things. We said D is a bit smaller than N. So this is D, this is N. Then U is a D by D matrix, and V is a N by N matrix. That's what the SVD is, and what we have done, we've just talked about all these columns of U, and we said that they are orthonormal, actually the rows as well, and the same holds for the other part. Okay, so that's all basically how to compute the SVD of a rectangular matrix X. Yeah. Now I just did it wrong, so we said D is smaller than N. So this is how the picture looks like. Okay, is that clear so far? And properties of U and V, orthonormal. And same for V. And they also square. And then what about S? So S is actually diagonal. So. And this is a bit weird because it's a rectangular matrix. So what do we mean by that? So what I want to say is that it only has entries here on the diagonal, and everything else is 0. So that's the S matrix. So that's nice, and we just need to actually understand that this is possible and how to compute it, and then how we can benefit from such a decomposition. Okay. So U and V we discussed, and I'll just give you a little bit of interpretation why this is interesting to have this property for U and V. So the interesting thing is that if you have a matrix which is orthonormal, which is the same as saying unitary is the same thing but saying it for complex numbers, but so here just think of orthonormal. So such matrices are interesting. So they are actually like rotation matrices. So they are square, right? So they take d-dimensional input, they rotate it, and then they get a d-dimensional output. So this is, every linear map does that, so this is also a linear map. But the interesting thing is that this is a rotation which preserves the length of everything. So it doesn't blow up things or doesn't make it shorter. So it's not, the interesting thing is not about so much about the rotation or not, but the interesting thing is that the norms are preserved. And that's what we have written in the equation here. So here is the norm of your input, here is the norm of your output. So it's kind of interesting that this is staying a constant. Why is it the case? Just write it out. What is the squared norm of my output? So here's the definition. It's x times u, which is the transpose of this thing. So you see that you have this u with itself in the middle. And that thing that we just saw, that's the identity matrix. So that's the d by d identity matrix. Actually, the notation we use is just d, I think. So therefore, it's equal to just x with itself, which is equal to the norm of x. So this is kind of nice. And so this is everything we need. I say orthogonal matrices are quite natural, orthonormal matrices even more so. Again, the orthogonal kind of means that the columns are independent because they're perpendicular. Okay, just to finish the naming, so one thing you need to remember is that the columns of U are called the singular vectors, and the columns of V are also called this. So the ones of U are called the left singular vectors, and then the columns of V are called the right singular vectors. This is what the SVD is. There is one more thing, that namely there is a kind of choice of order you do with your entries in S, which is the matrix in the middle. So these entries on the diagonal, you could reorder them, which just means that I will change the order of my blue vectors. So you could do that. We don't want that to happen, so we specify a particular order. We say that the entries in the diagonal of S, they are ordered by magnitude. So they are sorted. Biggest one first, and smallest one at the end. So these entries they call the singular values, so of this thing. So these are the entries of the matrix S. So these are the diagonal entries of S, and they are sorted. And another very interesting thing is that they are all bigger than 1. Sorry, they're all bigger or equal than 0. So, so they're non-negative, sorry. So they can be 0, but they cannot be negative. So that's very important. The singular values. So they go from 1 to the smaller dimension. You can see this again in the picture. So n is bigger than d. But how many of them are there? There are only d, because the diagonal only has d elements, so which is the shorter of the two sides. I mean, if n would be shorter, then it would have n entries. But d is shorter, therefore the diagonal matrix has d entries. Does that make sense? Okay. So that would be nice to have such a decomposition. So does it actually exist? Can we find it and can we use it? And the answer, of course, is yes. I guess you have seen this before. So, and that's, yeah, let's just assume for now that we can compute the SVD. It actually is quite easy there. It's provided in every linear algebra package. It's also provided in SciPy and in MATLAB, of course, or anything you might want to use. If you need this, then you can give X matrix, and you will get as a response, the answer is going to be these three matrices, U, S, and V. Okay, how is this useful for dimensionality reduction? So later we will go back a bit to the properties of it. So if you have a data matrix now, a data set, so then we said we want to do this, that we go from D is a bit too high for us, we would like to reduce the dimension. We would like to go from, so this is kind of the goal, so so this is our original X. We want to find a X tilde, or I don't know how you want to call it, which, so the previous one had D entries. So let me use these colors. From D rows, you want to reduce this to K rows. So that's what you're trying to do, to reduce the dimensionality. Okay, how can we do this? So that's not going to be obvious yet from this slide, but we want to do this using linear transforms only. So what we kind of ask is, can we find a linear transform? So that's just a matrix, which takes X and maps it to this X tilde. And that's called the compression matrix. So this is the compression matrix. So the C here stands for compression. And yeah, what you want from this C, so you would like to have that it takes X and makes this a K, so a K rows matrix. So actually the C matrix, what's the easiest thing to achieve that it can take the X matrix and make it have just K rows? Well, it's very easy. You can just make it have K rows itself. And how many columns does it need? It needs D columns. Why? Because you want to multiply it with X. So you can, if you make your C matrix to have this form, K by D, then it will do the job. It will reduce, it will do exactly what we had written here. It will reduce our matrix with many, many rows, D of them, it will reduce them to k rows. So that's kind of nice. Let's try to find such a good C matrix. We haven't talked about yet what values we should put in this C matrix. That's actually, matrices like this are called a bit like a projection matrix sometimes. Because it goes down from a very high dimension, it goes to a lower dimensional space, so from D to K. So that's very nice. But to manage this, to manage the quality, we also need to be able to go back. So I don't just want to go one way. I mean, I could just set my C matrix to all zeros. That's not the point. But the point is I want something which works both ways. I can compress, and then I can decompress again. And the decompression, that's called R, which means a reconstruction. So this is kind of the decompression thing. And the R matrix, I want it to be of what form? So now this one takes a K, a matrix of K rows, and it should get it up again to D rows. So we'll have just the opposite dimensions. You'll have many rows and not so many columns. So this would be nice if this would work. So question is, can we find good matrices C and R, compression and reconstruction? So we also actually, we want to have this small error, and the error here we measure, this is what people call the reconstruction error. The most natural thing is just to use the squared error on each entry, and that's what the Frobenius norm is. You have seen this, right? So if you want to compare two matrices, the X matrix and another one, look at the Frobenius norm, which is the sum of all square differences. That's what you're going to measure. Question is now, find me the best R and C, which so in the sense that they have the smallest reconstruction error. That's what you're going to do now. So okay, we will dive a bit into the math. But what this is saying that you can actually use the SVD to do this. So if we say that this is your problem, you want to find the best R and C, then this is a very interesting lemma here. It kind of gives you R and C's and says that these are kind of optimal. So let's see what we have here. So let's first talk about the compression and the reconstruction thing. So here you can see the compression matrix, so that's your C. The C is UK transpose. So UK is the first K columns of your U matrix. So these are the first K singular vectors, if you remember the picture. So the light blue columns, these are the first 4 singular vectors. So UK is these guys. I can actually write it here. So this is UK. It's a K by D matrix, right? We have just 4 entries here, so it's K equal 4. And yeah, it turns out this matrix is our compression matrix. That's the C matrix. Then the reconstruction matrix is the same thing as well, but it's transposed. So UK is also the reconstruction matrix. Okay, so now this lemma is talking about this reconstruction error, so this Frobenius norm here, it's saying this is actually small. So how small? It's saying that this reconstruction error is the best you can get. It's smaller than any reconstruction error for any rank K matrix. So now we also see what the whole lemma is talking about. So it's talking about rank K matrices. So this is this X hat thing. so any x hat, so any matrix of rank k, you find it, it will have a worse reconstruction error than what I just told you, the one we got from the SVD. So that's what you have here, right? The reconstruction error from any given matrix, as long as you restrict yourself to rank k, then the reconstruction error, which is here, is worse than what we get from the SVD, which is in the middle. Does that make sense? So this is very interesting and kind of surprising that there really is no better R reconstruction and C compression. So actually, so why this? Do you guys see why this has a rank is rank K? So the green part, which is the product of all these three matrices, that's actually a rank K matrix. That's very easy to see because it's K columns multiplied with the purple stuff. So it's K columns multiplied with the matrix. So therefore you have found a rank K factorization. It has, yes, because UK only has K columns. That's why this is a rank K matrix. You can think about this like, yeah, if you multiply matrices, then the rank only goes down, which is kind of what we see here. So the K columns which get multiplied. Okay, well, just to recap what I said is this from the SVD, you get this UK, the first K singular vectors, that's your UK. This is your reconstruction matrix, and it's also your compression matrix if you transpose it, and they are the best. There is no better approximation to your X matrix in the Frobenius norm. So there is a second part to the lemma, which I just touched briefly. It's also telling you that, by the way, we can say something about this reconstruction error. We can actually quantify it. So first of all, the reconstruction error is not zero. It's actually the sum of the singular values squared, but which ones? That's crucial here. So it's the sum of those values which are after the k, right? So you can kind of think about it, the first k ones, you get them perfectly. There you don't get error, that's the intuition. So in these directions you're perfect. So if you have chosen this k dimensions, it kind of makes sense that in the, so UK, in that space, you are perfect because that's how the UK is defined. But on the others, you have an error. So the ones which come after k, that's from k plus 1 and so on up to d, which is the smaller of d and n. So there is still an error. And now you can see the more k you take, the smaller this error gets, because then there will be less participants in this sum on the upper right. But this lemma is true for k equal 1. Then what it tells you is what is the best rank 1 approximation to your data. And it tells you, yes, it is the first singular vector. And it also tells you that the error to it is actually all the singular values from 2, 3, 4 up to d, if you sum up these. If you're interested in the error, maybe you're not even interested in the error, maybe you're happy already that you got the best U and the best reconstruction matrix and the best compression matrix. So, okay, a proof of that is not so hard, but this is a very fundamental result. And if you're interested, you can have a look at the proof at the end of the lecture notes. But what's maybe even more important about this than the proof is that now we have found a way to use this technique to compress data, right? To reduce the dimensionality of our data set. That's the important thing here. So the X matrix, remember data points are columns, they had too many features, they had D features. Now we have managed to project it down to K features, and we found that it's still very close. So the one projected down to K features is actually the compressed one here in purple. and we were able to say how close that is to the original data. So I'll come back to that in a minute. But is there any question on this lemma? It's maybe more a theorem, but it's actually not so hard to prove. Okay, so that's how to use it for dimensionality reduction. And again, the cool thing is you only need the left singular vectors for this. You don't need a V, so that makes life a bit easier. Compute the SVD, take the UK, and that's your dimensionality reduction. So what it's saying is that the most important information of your data is preserved in the first few singular vectors. Sorry. So, and this is precisely how much it is preserved. So, and so also they are orthogonal to each other. So these are kind of the directions which are most important to describe your data. Then they're independent, and how well they describe your data, that's quantified in this lemma. So these singular values, which are the SIs here, I think that's maybe a typo because we call them, no, that's SI, these are the diagonal elements of S, that's correct. So they quantify how close you are to the best rank K approximation for any K you like. So K can be from 1 up to D. If you set K to D, then it's also very easy to see, you can check that then you will get 0 error, then you get perfect approximation. If you want a little exercise, that's something you can try. Okay, so again, it's not so much about making mathematical statements, but the important thing from this is that this defines what principal component analysis is. So this is PCA. So here, principal component analysis, which is called PCA. And what we will do next is to try to understand better how to interpret this. So do these vectors actually have a clear interpretation or not? And I can tell you they do. So do we have time? Okay, let's see a bit. So the SVD, we have computed the whole SVD for all values. Well, there are D entries, which are these S entries, the singular values. But then we have only used the first K of them. That's a bit strange. So what does that mean? So what we have actually done is what's written on this line, and I will come back to this after the break. But what we have done here, this is a very important equation here, is that it's a bit strange here, right? That why would you take this U matrix to multiply with itself? That's what was this reconstruction after compression thing, right? So what we see here is that that's actually the same as to use the full SVD, but then to throw away all the singular values which are after K. So you only keep the first K singular values. So this SK matrix here is crucial. SK. What it is it's again this diagonal matrix, but it's forgetting the all entries except the first K on the diagonal. So here we have just put zeros. So and everything else is 0 anyway. So this is this small matrix which just compares, which just remembers the S1 to SK. And so what that does is, Well, that it only uses the first k singular vectors, the left singular vectors, and it only uses the first k right singular vectors from the V. So that's what this equality here means. And after the break, I'll explain again to make sure that we're really on the same page with these two equalities here. Okay, let's take a short break.